Hey everybody. In this video we're looking at how to deal with inclined planes, and this is going to be very important for the lab that we do on Thursday and Friday depending on what class you're in, or Thursday and Friday if you're in first hour. We want to be able to do a free body diagram for an object that's on an inclined plane. In the lab it's going to be moving at a constant speed, and it'll be very similar to the friction lab we did the week prior, where we were looking for mu k, the coefficient of kinetic friction. You'll end up doing the same thing, but now you're going to be dragging a block up an incline at a constant speed. So with this lab, it's very important that we go about diagramming the forces that are acting on our object and think about how certain forces are balancing out and how to write that as an equation. So we'll start with this first picture I have here is just very similar to what we saw at the very beginning of forces when we did our free body diagram stations that you went around to. I have an inclined plane here, and there is a tape dispenser that is just sitting at rest on our inclined plane. It's not moving, so this tape dispenser is at rest. At rest. And so if I'm just looking at that and I see, okay, the object is at rest on this inclined plane, that tells me that the acceleration is 0, which therefore also tells me that the net force, or sigma f, is also 0, which another way of saying that is that all of the forces must balance out. All forces balance. Like in our previous friction lab where we were dragging the block across the table at a constant speed, in that lab all the forces balanced out. It'll be the same thing for our new lab with the inclined plane, except we have some other forces acting at angles, so we have to be careful. It makes it a little more challenging. I'm going to use the light blue color here that you see to draw in where my axes, my x and y axes, are going to be. And because this thing is not horizontal, sitting on a horizontal surface, because the surface is at an angle, I'm going to actually tilt my axes so that they line up with the plane, which seems to be at about 35 degrees or something like that. So here's one of my axes that I'm going to use, and this is going to help me draw my free body diagram accurately. Remember, our free body diagram is just going to be a dot for our object and then arrows showing the forces acting on that object. So there's 33 degrees, seems to be the incline, and that's going to be one axis. My other axis I'm going to do perpendicular to it. So all I'm doing here is I'm kind of rotating the frame of reference. Instead of x and y being like this, I've rotated them to be like that because it's going to help us. It's going to make it a little easier. So this blue line that I've drawn perpendicular to the plane, I'm going to call the y-axis, right? Because that's what was vertical, but now it's tilted because we're inclined. So I'm going to call this that's the positive y direction, positive y direction, which means down here this would also be the y-axis, but this would be the negative y direction. One direction is positive, the other is negative. And then you can guess, since that's the y-axis, the other one's going to be the x-axis. So this is the x-axis over here, and so I'm calling this direction up and to the left from your perspective, looking at the screen, up the incline to the left. That's gonna be my positive x-axis, or positive x direction. And then down here on the bottom right, that's also the x-axis, but this is going to be in the negative direction. So this direction is going to be the negative x direction. Nothing special we've done here. We've just tilted our axes to match our inclined plane, and we do that because it makes things more convenient when we have the axes lined up with the actual surface. Okay, so I've got that in there. I'm going to represent my tape dispenser with a purple dot. So I'm just going to say that's the dot representing my tape dispenser. And now I need to do a diagram of the forces acting on my tape dispenser. So I'm going to do my forces in orange. One force we know is going to be going straight down to the center of the earth. So that's going to be the force of gravity. Let's make it nice and long so this is clear. So here's Fg. And remember, Fg always equals what? Mg. Thank you. All right, another force acting on this object. Think of it. What's another one that must be acting on it? we know from our stations we saw similar things to this. We got a surface, that's the inclined plane, pushing up to the right. See how it's the normal force here, that's our normal force, Fn, is going to be perpendicular to the surface, so we already have the y-axis lined up directly with our normal force, and that helps make things easier. That's one of the reasons why we've tilted our axes. Okay, so we've got gravity pulling straight down, normal force, and the last thing we need here is going to be our static friction. This is not moving. There's got to be some friction there. That's what those little rubber things on the bottom of the tape dispenser are for, right? They keep it from sliding around. Okay, so my static friction, or Fs, is pointing up the incline in the positive x direction. Notice how my friction is now parallel to one of the axes that I've made. Normal force is parallel to the y-axis. Static friction is parallel to the x-axis. That's one of the reasons why we've rotated the axes. Okay, so now we have our free body diagram here. We've got nothing else acting on it. And we know static friction points in that direction because we imagine if the inclined plane were frictionless, which way would the tape dispenser be accelerating? It would be accelerating down the incline, and so the static friction must be pointing in the opposite direction. That's all that is here for this one. So there's one thing we gotta do, which we've done before with projectiles, and that's when we have a vector arrow. For projectiles, it was launch velocity at an angle. We had to break it into its horizontal piece and its vertical piece when it's launched at an angle. Now we're going to have a force at an angle, or a force that is not perfectly lined up with one of our axes. In this case, that's Fg. See how Fg is just pointing off somewhere into one of the quadrants of the axes grid. It's not parallel. It's not, Fg is not lined up with the x or the y axis. So we're going to have to break up Fg into its two components or parts, the x part and the y part. So I'm going to take this stuff that I've just made, I'm going to move it off of my picture so we can abstract it a bit. So here's our free body diagram. I like to sometimes put in this other line right here to show that this is the angle theta that we've inclined our plane. Having the little dotted lines there for the axes and doing that little bottom of the incline there like I've done, I think is a little helpful when you don't have the rest of the picture there. You're just doing the free body diagram. But you can see we've just pulled over our free body diagram off of the actual picture. And here we go. So we only have one force here that is not perfectly lined up with the x or y axis. That's the force of gravity Fg. So I want to make a right-angled triangle out of this Fg, where the Fg arrow that's pointing straight down is going to be the hypotenuse. So I'm going to use green here to represent the force. So it would be like the component or part of Fg that's parallel to the y-axis. I'm going to do that in green, and I'm going to keep it in dotted lines all the way down to where the arrow is, which looks like about there. And I got an arrow. All right, so this would be in green the force of gravity in the y direction, because remember I've called that the y-axis, and that's actually pointing in the negative y direction, because we've called in that downward left direction of the y-axis the negative direction. And then I've got in red the horizontal component, or the x component. Okay. All right, so again, I'm going to put it in dotted lines like I did with the projectiles, where we found the horizontal and vertical components of the launch velocity. This is the same thing. We end up with a right angle here, because I have one component or part of Fg, one part of the orange Fg force vector is parallel to the y-axis. That's what's in green. And then the other one in red is the force of gravity in the x direction, which is pointing down along the incline in the negative x direction. And so I've labeled each of those pieces. Like we did with our projectiles when we found the horizontal and vertical pieces, we had to say that they were vi sine theta, vi cosine theta, because we're using the properties of the right-angled triangle to be able to give a specific quantitative amount to each of these two parts, the green and the red part. In our inclined plane, this angle theta, this is right there, that angle theta, which is how much you incline the plane. So we're at about 33 degrees or 35 degrees or so is how much this plane is inclined. That angle right there is equivalent to the angle right here in our right-angled triangle that has the gravitational force. So you're going to go and have to draw this when we do the lab on Thursday or Friday. And you need to know where that angle is. It's going to be right up there, adjacent to your FGY and the full hypotenuse, the full force of gravity that's going straight down. It's not the angle down here. No. And we can do a geometric proof for that, but I'm not doing that right now. Okay, so if we know where our angle theta is, now we can name each of these two parts, the force of gravity in the y direction and the force of gravity in the x direction. All I got to do, I'm going to look at my triangle, and I see that FGY, which is in green, is adjacent to my angle. So we think, what cosine or sine, which one is there to relate adjacent to hypotenuse? That's the cosine. So this one's going to be force of gravity times the cosine of that angle theta. That's going to be equal to FGY because it's adjacent to that angle. Similarly, with our red x-axis component, FG in the x direction is going to be the hypotenuse, the full FG in orange, times the sine of that angle theta because it's opposite. It's on the opposite side of that angle. We always know FG is equal to mg. So I can write this one more time. I'll write it for the red x direction first. That's going to be mg, because mg equals fg, mg sine theta. All right, so this is an important expression that I need for the component of gravity that's pointing down along the plane. And then I can do the same thing over here for my fgy. It's going to be mg cosine theta. mg cosine theta is the force of gravity in the y direction. We've got to break the gravitational force in orange, Fg. We have to break it up into those two pieces, horizontal and vertical, if you are switching your perspective, or we can just say the y component and the x component. After we've done this, now we can really start, only at this point, can we start to write equations to show how things are balancing out. So let's just look at the y-axis. Focus your attention just on the y-axis. I have a force, a normal force. Whoa, what is that? Focusing just on the y-axis, we have a normal force that is pointing in the positive direction. Go back and look at our dude over here. Our tape measure is just sitting there. Everything is balancing out. So that means everything in the y-axis direction, or maybe it's this way from your perspective, everything in the y-axis has to balance out. Everything in the x-axis has to balance out. Otherwise, the forces wouldn't be balanced and you'd have an acceleration. But this thing has an acceleration of 0, so all forces must balance. It's just sitting there. That's the same. The same is true if it's moving at a constant speed. All the forces must balance. Okay, so we're looking at the y-axis over here. Normal force is pointing in the positive y direction. In the negative y direction, I just have my green dotted line. Once we break up that orange FG into its y and x components, you don't look at the orange FG anymore. You've got it into its pieces. So all we're looking at are the green and the red pieces once we start looking at the x and y axes. So these two guys are balancing out. It must be the case in the y direction that those two forces balance out because those are the only forces in the y direction. So in y direction, we can say, let's put a little arrow here, normal force must be equal to FGY. And then if we use the correct placement of that angle theta, then we know that FGY can also be expressed as mg cosine theta. Okay, here's one true statement we can say about this system, this situation, this scenario, whatever you're looking at with the forces on the incline. Right now, one true statement we can write is that the normal force in this scenario must be equal to mg times the cosine of the angle theta. And think about that. As the angle theta is changing, the normal force is also changing. So if we go all the way down to 0 degrees, say if theta equals 0 degrees, That means we don't have an incline, we just have our object sitting right there with the force of gravity going straight down. This is an incline of 0 degrees, it's just horizontal. And we'd have the normal force going straight up, and they'd have to balance, right? So we look at this equation, see if it makes sense. If theta equals 0, then that means we'd have the cosine of 0 degrees. The cosine of 0 degrees is 1, right? So if theta equals 0 degrees, then cosine 0 degrees equals 1, then the normal force would be equal to mg times 1, or the normal force would be just equal to mg. So this equation that I've boxed in purple makes sense. It's just telling you how much the normal force is pushing up on this object, and it changes as you change the angle. If you make the angle 0 degrees, then you get all of the normal force is going to be balancing with all of the force of gravity. All right, so that's kind of an aside, just to make it like a logic check on our expression we got there. Let's just move that to the side for a minute. That was in the y direction. Then we're going to look at in the x direction. Once we've broken stuff up into the x and y directions, we're just looking to see, hey, okay, if the acceleration is 0, all this stuff needs to balance out. So now we're looking at the x direction. Let me change my color here to like a pink, I suppose. So I look in the x direction, what's parallel to the x-axis. I see static friction pointing in one direction, and then I can't forget about my component of gravity also pointing in the x direction, but the negative x direction down there. The force of gravity in the x direction. So in the x direction, we have forces that are balancing out because the acceleration is 0. So I've got static friction, Fs equals Fg in the x direction. And if we've set up our triangle properly over here with theta in the correct spot, then we know that we can express Fg in the x direction as mg sine theta. So I can write that once more as mg times the sine of that inclination angle theta. And there's another true statement that I have about this scenario. All we've done, the main thing that we have to do is make sure that we break up that force of gravity into its x and y components or parts. And the y component, as you see over there in green, is going to be mg cosine theta because of where that angle theta is in the triangle we made. The force of gravity in the x direction is going to be mg sine theta because of where that angle theta is in the triangle we made. Fgx is opposite that angle. So now I have two true statements in purple and pink that can be used to try to solve a problem. In the lab that we do, we're going to have a block, a wooden block like we had before that we dragged across the table horizontally. We pulled it at a constant speed, so we knew that kinetic friction in one direction was balancing with your pulling force that was measured on the force sensor. We're going to use the force sensors again. So you're going to have a block here, and we're going to have a string to help you pull it. This really should be about 35. Okay, so let's say our string, I'll just draw in gray, is attached to my block, and it's going up, and it goes around this pulley. And then we're going to pull that force sensor downward. So you'll exert some force, call it it could be the force of tension from the string, whatever you want to call it, an applied force. You're going to be pulling on that force sensor so that the block moves up the incline at a constant speed. So the block is moving up the incline at constant speed, just like we dragged it at a constant speed across the horizontal table in the previous friction lab. So constant speed, you got to remember. Okay, constant speed means acceleration is what? 0. It's not speeding up, it's not slowing down, it's not changing direction. Acceleration is 0, which means net force is going to be 0, which means all forces balance out. Okay, sounds familiar, right, to that previous one we just did. All the forces got to balance out. But what's different? Here we had static friction, right? Because the tape dispenser is just sitting there not moving. In our lab, you're going to be dragging this block up the incline. So if it's moving at a constant speed, it's not going to be static friction. What's it going to be? In that lab, your objective is to figure out mu k. Once again, you're trying to figure out mu k. And you are going to need to produce a graph again like we did so that you can figure out mu k from the slope. So let's take a look at what our free body diagram would look like for this very lab. So here's the normal force. We know that's going to be perpendicular. We've got our force of gravity, Fg. We always know that equals mg. You're going to know the mass of your block, just like we did last time. We had the block, and then we put more and more weights on top, and we got better data the more mass you had on top of that block. So you probably don't want to be doing this one with just the block and a 90 gram block. Put a bunch of weights in there. We'll keep increasing the weight or the total mass and to get our data points just like we did last time. Only difference is now we got this thing at an angle. All right, what else is going on? We're sliding up the incline. You call that the tension force from our string. Okay, and then what else? We got something else there. Tension's the applied force pulling it up the incline. We also have kinetic friction going in the other direction. Okay, so there are all the forces acting on our wooden block as it's sliding up at a constant speed. Up the incline, we've got tension in the direction of its motion because we're pulling it at a constant speed. We've got our Fk. You could probably call this your applied force. Change that because your applied force is pulling down on the force sensor and the tension is pulling up. Nothing's accelerating, so these got to balance out. All right, you got a tension force pulling on your block, so it goes up the incline. Kinetic friction's in the opposite direction. Fg is pointing straight down, which always equals mg, and you got a normal force going off at an angle. So we do an actual free body diagram for this. We want to have those axes. So we have that free body diagram, and then we got to do what we did before, just in the previous example. We need to break Fg up into its y and x component parts, its pieces. So I'm going to draw dotted lines. The green one I keep along the y-axis. So that's the force of gravity in the y direction. Remember, our angle theta is right up there. We've got our red or x component of gravity, Fgx, down there. And now our free body diagram also has those component parts of the gravitational force. So Fg in the x direction we know is going to be mg sine theta because it's opposite that angle. Fgy is going to be mg cosine theta because it's adjacent to that angle theta. And now we've got everything mapped out. So when we go to apply our second law, which remember we can go like we just said in the previous one, you can look at the y-axis or the y direction. You can look at the x-axis or the x direction. And so we're applying that second law, F equals ma, but the acceleration is 0, so we know that all the forces in each direction, respectively, should balance out. In the y direction, I've got normal force, that's in the positive y direction. And now that I've broken Fg up into its y and x component parts, then green and red, I don't look at the full Fg in orange anymore. I'm looking at the pieces. So what's directly opposite normal force is our green force of gravity in the y direction. That's the same as we said last time in our previous example. So we know normal force must be equal to the force of gravity in the y direction. But we know how to express that with mg and the angle. That's mg cosine theta. All right, so there's one true statement that we have. And then we look at the x direction, which I've done in pink, so here it comes. And the x direction, I've got the tension force in the positive x direction that's trying to bring the block up the incline. We have, don't forget about friction, there it is sitting there in the opposite direction, so they're fighting against each other. And then we also have our red component of gravitational force also pointing in the x direction, downwards, down the incline like kinetic friction is. So when we come over here, I can say, what forces need to balance? Well, I've got tension force pointing up the incline. So that's a force going up the incline. And then I have two forces pointing down the incline. Kinetic friction, Fk, and the red x component of gravity, which is mg sine theta. So I've got force of tension in one direction. It needs to balance with the other two forces going in the other direction. So Ft equals the kinetic friction plus the tension force also needs to be balancing with the force of gravity in that x direction. So we're just listing all the stuff that points in the positive direction is on one side of the equal sign, and then all the stuff that's pointing in the negative direction is on the other side of the equal sign, because they have to all balance out. Now we can write Ft is going to be Ft, and then we've got Fk for kinetic friction. We know we can write Fg in the x direction as mg sine theta. We're going to know that our force of tension, like with our previous friction lab, I can go back to our diagram over here. If the acceleration is 0, then the force of tension is going to be equivalent to what the reading is on the force sensor. So we're going to know what that is. That's actually something you can just record in your data table. The force of tension that's pulling the block up the incline, that's equivalent to the force in the force sensor, because it has to balance with the tension force as you're dragging the thing. So we're going to be able to measure Ft. You're going to be able to find mg sine theta, because you're going to know theta and you're going to know the mass of your block and all the other mass you might put on top of it. The last thing you need to think about is like, okay, if I'm trying to find mu k, which is the objective of the lab, what is Fk equal to? And that's another equation that we use. We used it in the first friction lab. Fk equals mu k times the normal force. So your objective is going to be then to take these couple of equations, true statements we have about what's happening in the x and y axes for our block, and figure out how you can figure out what mu k is. And you need to be able to draw our diagrams for inclines and look at what's balancing with what in each direction or on each axis. All right, that should help a bit. See you next time.